Okay, so we have to prove the derangement of n symbols as an is equal to n factorial 1 minus 1 by 1 factorial plus 1 by 2 factorial minus etc. plus minus 1 the whole power n by n factorial. So this is what we have to prove. So for that, let's know the term derangement. So what is derangement? It is a permutation of element of a set in such a way that no element should appear in its original position. So what does that mean? If you arrange the given elements and if you say the arrangement as a derangement, then the element should arrange in such a way that no element should appear in its original position. So essentially the formula would be practically speaking, derangement of n elements is equal to total number of permutations of n elements minus number of permutations in which at least one of the element occurs in original position. So now total number of permutation is we can arrange element according to whatever way we want. So if you subtract from that number of permutations in which at least one element is in original position, you can say that this is a formula essentially for number of elements in which no element should occur in its original position. Okay, so for example, if you consider an object and if you say that it possesses the ith property, it means that that should be represented as n of I. That means the ith symbol is in ith place. So for example, if you consider 1, 2, 3, 4, alright, let me take my pen. 1, 3, 4, 4, and if you say the second position is preserved, so what does that mean? The second element should appear in the second place. So if you see the two arrangements, the second element, that is the 2, appears in its original position, and hence you can say this arrangement for this is a derangement. Okay, and next therefore, n of I is equal to number of permutations of n minus 1 symbols. Why n minus 1 symbols? Why n minus 1 symbols? Because if you say n of I, the ith place is preserved. So, one position, the ith symbol, the symbol, ith position is preserved. So, hence, if ith place is preserved, then you can say the remaining n minus 1 symbols. So, among n symbols, one place is preserved. So, the remaining n minus 1 symbols can be permutated in n minus 1 ways, that is n minus 1 factorial. Therefore, n of 1 plus n of 2 plus n of n is equal to nc1 into n factorial, because there are total n among n elements. One element is preserved, that is nc1, and the remaining n minus 1 elements can be permutated into n minus 1 factorial ways. Similarly, if you take n of 1 I comma j, the ith and the jth position is preserved, and hence it denotes the ith and jth symbols, and n of I comma j is equal to number of permutations of n minus 2 symbols, while 2 symbols are preserved. So, the remaining n minus 2 symbols can be permutated in n minus 2 ways, that is n minus 2 factorial for all j is equal to 1, 2, 3, etc. n. Since 2 symbols are fixed, leaving n minus 2 symbols to be permutated. Therefore, n of 1, 2, etc. n of n minus 1, n is equal to nc2, that is among n symbols, 2 symbols are preserved, that is nc2, and remaining n minus 2 symbols can be permutated in n minus 2 factorial ways, and so on. Now, according to the principle of inclusion and exclusion, so already we have learned the principle of inclusion and exclusion. What does the principle of inclusion and exclusion means? It means at least one of the, it should preserve at least one of the n properties. So, you have the formula, right? At least one of the n properties will be n of 1 plus n of 2 plus etc. n of n minus n of so plus minus etc and so on, right? So this is of like A plus B plus C is equal to, sorry, I beg your pardon, minus A intersection B minus, so essentially to write it will be like B intersection C. This is a formula for inclusion and exclusion principle. Okay, C intersection A, and then plus what will come, A intersection B intersection C, like that it will be so on. So in that procedure, following this, we are writing this formula. Okay, so the next one, so substituting all the values that we have found, so in NC1, NC2, NC3 and etc minus 1 the whole power n minus 1, because we don't know what symbol will come at this place, so whole power n minus 1 NCn n minus n factorial. So if you simplify this, NC1 is n by 1 factorial, this is n into n minus 2, n minus 1 by 2 factorial, n into n minus 1. So the last term will be minus 1 the whole power n minus 1, NCn is 1, n minus n the whole factorial. So multiplying and dividing by n factorial. So if you multiply and divide by n factorial, you will get n factorial 1 minus, because n factorial will get cancelled. So the multiplying term will be outside, the whole power n minus 1 by n factorial. Okay. Now we have to find the derangement. So already I have told what is derangement. The one position will be preserved, that is no symbol should occur in its original position. The formula will be total number of permutations of n symbols minus number of permutations of at least one of the nth property, number of object that possess at least one of the n properties will give me the number of derangement, that is number of object which possess none of the n properties. So it would be n factorial, which is why n factorial, total number of permutations, right? So total number of permutations n factorial minus n factorial 1 minus factorial etc minus 1 the whole power n minus 1 by n factorial. Therefore a n is equal to n factorial, if you take common 1 minus, multiply it inside. So this is what we have to prove. So we have proved. Isn't that easy? The one concept that you should remember is only one concept, which is n of I, that is the ith symbol will present in the ith place. Therefore the object is possessing the ith property. So that is what we have to learn, we have to understand in this proof.